Welcome back to the workshop. It's Tim for Tim Cross Electronics, and this is going to be a little bit of a different video. This is kind of just an introductory, talking about some of the more technical aspects, design choices that I made for the Voxer amp that I'm going to be working on. This is not, there's no building in this video. I'm just talking about technical stuff, so if you're looking for a build video, you may want to skip this, but if you want a better understanding of power transformer or output transformer primaries and technical stuff like that, then I think you might find this interesting. So I'm going to start by talking about the power differences between a Deluxe Reverb and a Princeton Reverb, and I'll also talk about the Vox AC15 versus the AC10. It'll be clear a little later why I'm getting into that. Also, you'll have to apologize. You'll have to forgive me if I spend too much time looking at my notes here. This is a little bit more than I can memorize. The Deluxe Reverb is a 22 watt amp. The Princeton Reverb is a 15 watt amp. Well, it's marketed as a 15 watt amp. It may actually be closer to 12 watts. And there's been a lot of debate as to why there's a difference in power output from those two amplifiers. They're both very similar circuits. And there's, one of them's 22 watts, one of them is 12 or 15 watts. Now, doubling the power would only be an extra 3 decibels of output. You could easily make up for that by just changing the speaker. So it's not like there's a huge volume difference between the Princeton Reverb and the Deluxe Reverb. But as far as measurable output power goes, yes, there is a pretty big jump in power when you move up from the Princeton to the Deluxe. And it's similarly when you move from the Vox AC10 to the Vox AC15. So some people have theorized that the difference in power between the Princeton and Deluxe Reverbs may have something to do with the B+ voltage, because the Deluxe Reverb has 5 volts more at the B+ than the Princeton does. The Vox AC15 also has 5 volts more at the B+ than the AC10. However, your wall voltage is going to vary enough that at the secondary of the power transformer you're going to see a bigger difference than 5 volts anyway. And, in the case of the AC15 and AC10, since those are both cathode biased, they're seeing an even smaller difference than that. I don't think that the power difference has anything to do with that 5 volt change in B+ voltage. So maybe it's the phase inverter. The Deluxe Reverb has a long-tailed pair phase inverter. The Princeton Reverb has a cathodiene phase inverter. So it makes sense, if the cathodiene is typically used in lower powered amplifiers, the long-tailed pair is used in high power amplifiers. So you could easily look at that and say, oh, well, it's, the phase inverter doesn't push the power tubes as hard. However, if the phase inverter is capable of pushing the power tubes at all into clipping, then it can't be a limiting factor. Here's why. When we measure the output power of a tube amplifier, we're inputting a sine wave at the input of the amplifier, and then we're turning up the volume and measuring on an oscilloscope at the output secondary, and we're basically turning it up until just until the point where the power tubes start to clip. So we're only measuring a clean sine wave. That's the only thing that we care about when we're measuring the power output of an amplifier. So again, if the cathodiene phase inverter is capable of clipping the power tubes at all, then it's not limiting the output power. And we know that the Princeton Reverb can clip the power tubes quite well. In the case of the Vox AC15 and AC10, they both have a long-tailed pair phase inverter, so that can't have anything to do with the power differences in those two amplifiers. So maybe it's a difference in the power supply. I've seen it suggested that the power supply sag makes a big difference in the output power, and that may be the cause of the power drop that you see moving from a Deluxe Reverb to a Princeton Reverb. And that makes sense at first glance because, yeah, if you get a lot of power supply sag as you're driving the amplifier hard, you could see a good 50 volt drop in the power supply, or even more than that. you could see a pretty significant sag in the power supply when you're really pushing the amplifier hard. However, I don't think that has anything to do with it either. And this comes back again to the fact that when we're measuring the output voltage, we're measuring a clean sine wave. Now, power supply voltage that dynamically varies, dynamically drops and limits the output power as the tubes are driven hard is going to be seen as compression. And a compressed sine wave is not a clean sine wave anymore. So we would be able to see that compression on the oscilloscope, I would think. I could be wrong about that, but it seems to me you'd be able to see that compression. So, and you know, furthermore, just the fact that we have to push the amp hard in order to see that power supply sag, that alone tells me that we're not measuring clean power anymore. So I don't think it has anything to do with power supply sag either. So okay, what about the output transformer? There are two aspects of the output transformer that differ in the Princeton Reverb compared to the Deluxe Reverb. There's the physical size and the primary winding. If the windings of the output transformer can handle the current, but it has a smaller core, then the core will saturate and start to limit the output power. And this happens primarily in the low frequencies. In fact, Fender cleverly used this in the Tweed Deluxe. That's why the Tweed Deluxe and a lot of other vintage amplifiers, as you really crank them up, the low end starts to roll off and it takes on a little bit more high-end presence, a lot of mid-range emphasis when you're really hitting the power tubes hard. So that is a very real consequence of a smaller core in an output transformer. It does limit the output power. However, once again, it doesn't limit the output power before clipping. It limits the output power after clipping. We're still measuring a clean sine wave, so if that the output transformer is limiting the signal, again, that's going to present as compression, and so we're still not measuring a clean sine wave if we're measuring a compressed signal. So I don't think that core saturation has anything to do with the output power either. So that leaves the output transformer primary. And this is where we find some consistency between the power differences in the Deluxe Reverb and Princeton Reverb and the power differences between the AC15 and AC10. Okay, so the Deluxe Reverb has a primary impedance of between 6.5K and 6.7K. I've even seen some that claim a 7K. Whatever the case, it's lower, significantly lower than the Princeton Reverb's 8K primary impedance on the output transformer. Now, the impedance that the power tubes see is a reflection of the load that's connected at the secondary of the output transformer. So if you double the impedance at the output transformer secondary, you're also doubling the impedance that the tube sees on the primary. This change in reflected impedance has a big effect on the output power. And you'll see a lot of hi-fi amplifiers rated for multiple power levels depending on the speaker that's connected to it. For instance, you might see an amplifier that's rated for 40 watts with an 8 ohm load connected, but 80 watts with a 4 ohm load connected. The same thing happens in tube amplifiers. If you connect a higher resistance load at the output, you're going to drop the power. And because that's reflected at the primary of the output transformer, if you have a higher primary impedance on the output transformer, you're going to decrease the power. If you double that, theoretically, you should see half the power. And I'm interested, if any of you have done this experiment before, let me know in the comments what the result was, because theoretically, if you were to connect a 16 ohm speaker to an amplifier that wants to see an 8 ohm speaker, you should have a 3 decibel drop in volume, which means that you're cutting the power in half. So I'm interested. If you've ever done that experiment, let me know. I don't have a dB meter, otherwise I would try that. But if you do and you've tried that experiment, let me know how it turned out. Okay, so where does that power go? Well, by increasing the impedance, you're reducing the amount of current that can flow through the transformer. And since the voltage output swing of the power tubes does not depend on the output transformer primary impedance, then if you're dropping the amount of current that flows, you have to also be dropping the power output. Also, because not as much current is flowing, there's less energy to reinforce the low frequencies. And so what you end up hearing is an emphasis on the highs and mids. And a lot of people perceive that as kind of increased presence. And basically that's what you're going to get when you attach a 16 ohm speaker to an amp that's made for an 8 ohm speaker. And so of course the opposite happens when you connect that same amplifier to a 4 ohm load. It allows a lot more current to flow, and again, because the voltage swing at the plates of the power tubes does not depend on the load on those power tubes, if you increase the amount of current that's flowing, then you're also increasing the power output, which also means that you've got a lot more energy to reinforce those low frequencies. And people often perceive this as more of a mid-scooped tone because you've got a lot more fuller low end. Now the problem with underloading a transformer like that is that if it doesn't have enough windings, if it's not made to handle that extra heat, then you could end up burning up the transformer from all that extra current that's flowing. So if we look at the Deluxe Reverb output transformer primary and compare it to the Princeton Reverb primary, we see that the Princeton Reverb has about a 20% increase in primary impedance, which corresponds to a roughly 32% decrease in power output. If we look at the Vox AC15 and compare it to the AC10, we see that the AC10 has a 25% increase in primary impedance, which corresponds to a roughly 34% decrease in power output. Now these figures may not be totally accurate. I don't have these amplifiers here to measure their power output, and the rated power of an amplifier is often more a matter of marketing than engineering. Again, the Princeton Reverb is a good example. Is it really 15 watts? I don't know, but 15 sounded like a nice number to Fender. So regardless of that, there's a very clear and direct correlation between the primary impedance of the output transformer and the measured output of that amplifier. And I would say it's a fairly predictable one as well. So now on to why any of this is relevant. Okay. When I first designed this amplifier, the Foxer that we're going to be working on, it was supposed to be a hybrid between a Supro and a Vox with 6973 power tubes. Well, I couldn't find the right output transformer or even the right power transformer for this project. The right transformers are available, but everybody's out of stock. So I had to go with what I had on my shelf, which was a Deluxe Reverb output transformer. And initially I was going to just make it a 6V6 amplifier, and I thought, man, that's so boring. I've built so many 6V6 amps. I want to do something different. And it occurred to me that just because I'm using a Deluxe Reverb output transformer doesn't mean I have to use 6V6s. I could easily use 6L6s in that amplifier. Now, Neil Young he famously puts 6L6s in his Tweed Deluxe amplifier and has consequently had to replace output transformers more than once because those output transformers are not made to handle the extra current from 6L6 power tubes. But a lot of people have had very good luck using 6L6s in their Deluxe Reverbs. The Deluxe Reverb output transformer is much better suited to using 6L6 tubes than the Tweed Deluxe output transformer is. And this is where this becomes relevant to this build. When Fender designed the Deluxe Reverb, and I think this could be said for most blackface and silverface amplifiers, they designed it to be used with a second satellite speaker speaker cabinet. And so if you look at the back of the chassis, you've got your main speaker output, and then right next to it, wired in parallel with the main speaker, is an extension speaker jack. So the intention was, if you needed a little bit of extra power, if you're playing a big gig, you leave your internal speaker plugged in, you put that at one end of the stage, and then you plug in a second extension speaker cabinet and put that at the other end of the stage. And you have sound coming from both sides of the stage. Which means that the output transformer sees half of the total load it would normally see, and it should have, theoretically, twice as much power. So the output transformer is made to be underloaded. So that's why you can use 6L6s in a Deluxe Reverb without damaging the output transformer. So the other concern, of course, is whether the Deluxe Reverb power transformer can handle the extra current long term. The short answer is yes. Not simply because a lot of people have done it and it works, although, valid argument, but because we're going to be drawing a lot less current than a Deluxe Reverb normally would. A Deluxe Reverb uses 4 12AX7s and 2 12AT7s. Typically a 12AX7 plate draws about 3 milliamps of HT current, and 12AT7s draw about 6 milliamps per plate. Of course, the reverb driver is drawing a little bit more than that because of the way that it's wired up basically as a power tube. So that's a total of about 48 milliamps of HT current that the preamp is drawing on a Deluxe Reverb, somewhere around there. And for this build, I'm going to be using 3 12AX7s in the preamp for a total of 18 milliamps. So that's 30 milliamps of HT current that we're not going to be using in this build. So whatever extra current the 6L6s are drawing, it can easily handle that. So also in this build, we're going to be taking a little bit of extra stress off of the output transformer because this amplifier is going to be cathode biased. So it's only going to be putting out about 75% of the power that it would be if it were fixed bias. Now we're also presenting a slightly higher primary impedance than the ideal value from the 6L6 datasheets. Now there's been some debate, actually a lot of debate online about these ideal output transformer primary impedances. Just because the datasheet recommends a certain primary impedance doesn't mean that you have to stay close to that figure, and the Deluxe Reverb is a perfect example. The datasheet says that you should have a 7K primary impedance for a Deluxe Reverb. But when we use the extension speaker cabinet in a Deluxe Reverb, it's seeing a 3.3K load primary impedance. And it's, despite what people might tell you, the tubes aren't writhing in pain when that happens. It's doing just fine. So as long as the other factors involved can support a lower or higher primary impedance, you're just fine. Don't worry so much about getting the perfect primary impedance. There are plenty of other things involved in this equation. I usually start with the recommended impedance just to make things easier, so I don't have to do as much calculating later on to, figure out whether it'll work and what components need to be beefed up and so on. But remember that these data sheets were written by engineers, and they were essentially trying to get the greatest power output with the lowest THD from these tubes as possible. If you're building a hi-fi amplifier or test equipment, then yeah, harmonics are a really bad thing. But as guitarists, we like harmonics. Harmonics sound good. So high THD isn't a problem for us. It's a good thing. And a lot of amplifier manufacturers in kind of the classic era, they were looking to get as much power as they could out of those amplifiers because it was good marketing. If you could say that your amplifier was putting out 50 watts and somebody else's was only a 40 watt amplifier, then that's a selling point. These days, we don't want a lot of volume because we're miking everything. we don't need our amplifier to be incredibly powerful so that it can project all the way to the back of the stadium. And so we're not trying to squeeze every last watt out of these tubes. So use the recommended primary impedance as a starting point, as a loose guideline, but don't feel like you have to stick to it absolutely. The important things are, you know, can the transformer handle the extra current? And in this case, the Deluxe Reverb transformer definitely can. And are you going to burn up the power tubes? And no, we're not. This will be just fine. So finally, since I'm using a 5U4 rectifier rather than a GZ34, we're going to drop an extra, probably, I don't know, 20 volts on the B+, so that'll drop the power output a little as well. I'm expecting that we'll probably get about 30 watts out of this amplifier. It may end up even being a little bit lower than that. I mean, I'm not going to know until I actually get it working and I can measure the output. Now, it just so happens that the bias resistor that we need for 6L6, 6V6, and KT66 really aren't that far apart. So I can put an extra resistor in parallel with our main cathode resistor that will allow me to switch between those three tube types. So 6V6, 6L6, and KT66. And because the KT66 is a very wide bottle, I have to be careful with how I space the power tubes apart. I want to make sure that I've got enough room in there for airflow so that the heat doesn't build up. Okay, so onto the choke. In most Vox amplifiers, and I'm not an expert on Vox amplifiers, I haven't spent a lifetime looking at the schematics, but one thing that I have seen pretty consistently in Vox amplifiers is that they use a very large value of choke. And that makes sense because they're not using any negative feedback. And when you don't have negative feedback to decrease the noise at the output, a big choke really helps with that, with noise. And so Vox often uses, I've seen 10 Henry chokes, 15 Henry chokes. I think I even saw a 20 Henry choke in a Vox once. So that those big chokes really help with the noise floor. And in this case, because we've got a variable negative feedback control where we can, with that control all the way down, have no negative feedback, just like we'd see in a Vox, I'm going to be using a 15 Henry choke. And that should help with the noise floor a bit. So I just finished doing a video working on the chassis here, and so I'm going to put the link in the description below. Take some time and watch that video. I think you'll find it interesting. I'm looking forward to making some more progress on this. Thanks for watching, and we'll see you the next time.